Hi, my name is Martin Hjelm. I'm here to talk about learning human priors for task-constrained grasping. This is joint work with Carl-Henrik Ek, Renaud Detry, and Dennis Zakragits. I'm with the Royal Institute of Technology and the Center for Autonomous System and the Computer Vision and Active Perception Lab. So, let's say we're given a set of demonstrations of a set of grasps. We're also given a pod here and two grasps to choose from. We're told to pick one good grasp of these two for pouring from the pod. And the question then is, if we would want to build a system to answer similar questions to this, how should we do it? That is, how should we build a system that learns to place task-specific grasps given a set of demonstrations? So we can start by making some observations. Let's have a look at these cups, for example. Realize that similar objects should sort of be grasped in a similar way for the same task. And we also want the system to kind of generalize what in the representation of an object is important for the task-specific grasp. And then we would want to reuse previously learned knowledge for placing these grasps. If we go back to our little introductory problem here, let's say we let the teacher annotate the demonstrated grasps as good or bad for pouring, where green is good and red is bad. We can then say that we could choose the grasp from the two options that is most similar to the grasps that are good for pouring. The problem here is then what is similar. So standard way is to use distance as a proxy for similarity, whereas then close instances are more similar than instances that are far away from each other. The problem then is that if we represent the demonstrated grasp by a set of features, then different features will have different measures of similarity, and how can we weight these features together to get a good similarity measure? And as we increase the dimensions, also we will increase the susceptibility to noise. And this means that the part of the feature that actually determines the goodness of the grasp might be very similar, but that doesn't matter so much if we add up all the other parts. So if we rephrase that and think about it, what if we could learn a representation such that similar instances are close and non-similar instances are far away, in such a way that we could pick out the most relevant features for the tasks? If we learn this representation, what we could do with our two options here, we could re-represent them in the new representation and choose the grasp that is most similar here, which is obviously the right hand grasp, and place the grasp on pouring for the pot. Okay, so let's say we already learned this representation and we want to implement it into a system for use with robotic grasping. I will talk a bit about how we can learn this representation later on. So let's say we have this bottle here and we have a gripper and we want to place a task-specific grasp, that is, for example, a grasp for pouring from the bottle. We have a set of demonstrated grasps for the task and a label for each of one of them as positive or negative for the task. What we would start to do is actually synthesize grasp on the object. So for a set of positions on the object, OI, here we would generate a gripper configuration, GI, and for each of these synthesized grasps we would extract features, which we called XI. For each of the grasps, synthesized grasps, we extract features, XI, which would give us the set XG here. And from this set, we want to classify the grasp as either good or bad. And we can do this by using K-nearest neighbor in this new representation. We would get out a set of grasps that are good for pouring. Now, from this set of good grasps, we would actually want to pick the best one. And one way of specifying with the best one is to form a kernel density estimate over xt. So for each of the grasps in xg plus, we compute the probability condition on xt, but we make the conditioning independent of all but the k closest members to the point that we're trying to classify. And then we pick the best one for that grasp. Okay, so now I've shown you how this learned representation can fit into a system for learning task-specific grasps from demonstration, and I will now talk about how we can learn this representation from the data. So if we go back and we think about it again, we wanted to rephrase similarity to mean learn representation from the data, and we wanted a standard Euclidean metric, perhaps. We want similar instances to be close and non-similar instances to be far away. And we want similarity to be able to be defined by the demonstrator actually and be reflected in the representation in such a way that irrelevant features are actually removed. A starting point for this might be to learn a linear transformation of the feature space, for example like this. That gives us the qualities we asked for, and this enables us actually to apply Euclidean metric, which plays nicely with both the KNN and the KDE solution. So we define this linear transform here, L, and through some manipulation we get this Gramian matrix M, which is a positive semi-definite matrix. And this expression here, the last one, is actually what is called a Mahalanobis metric. And the Mahalanobis metric is actually a whitening transform when applied to Gaussian random variables. And there's a set of algorithms that actually tries to learn M given some conditions on the set of points. And the one we use in this paper is the large margin nearest neighbor. And LMNM sets up the problem in the following way. Let's say we have a set of classes. We have a grasp class 1, grasp class 2, and grasp class 3. And for each point in each class, we define a target and its target neighbors. And for each of the target's neighbors, we want to define a transform that pushes the target's neighbors towards the center of the target. We also have a set of points that we call imposters. And imposters we want to push out outside a perimeter of the target neighborhood. In a way that's depicted here. And this can be formulated as a semi-definite program, where the first term here is the sum over the target neighborhood distances, and the second part is the violation of the margin of the imposters. I will not go into the optimization procedure here, but what I can say is what you can do is you can condition the optimization procedure in such a way that you learn a diagonal matrix. And what happens then is that these diagonal matrix elements are essentially learned feature weights for each of the dimensions. And so implicitly this facilitates then a sort of like a feature selection process, which allows then the system to kind of self-regulate and remove irrelevant features. And what's nice about this algorithm also is that you can actually specify which points are the target neighbors. So a demonstrator can then define its own similarity, and we can find that transform in that space, which is really nice. And so I will talk a bit about our experiments for this paper also. So we set up our experiments in the following way. We define a set of features that would capture color, form, etc. We define a set of tasks, which we call pouring, which is grasp place for pouring. a task which is called lift up, which is essentially top grasps, handle grasps, and grasps placed on corks, which we call cork. And first we will look at the learned matrix diagonal, and then we will look at quantitatively how the LMNN algorithm orders the grasps as actually compared to the KNN, for example, and the only Euclidean metric. And then finally we'll look at some synthesized grasps used for robotic grasping. So what we see in the diagrams here is the mean value and standard deviation of the elements in the diagonal matrix for each of the features. So we kind of summarize them by taking the mean of the matrix elements. A low value means a feature that's irrelevant for the task. A high value means a feature that is relevant for the task. So there are also some features that are close to 1 but with low standard deviation, and this means, for example, that the feature is considered as constant or ever present, that is a must for the specific task, which you can see sort of in the right corner here. So if we look at pouring, for example, we can see that the opening feature, the gradient filters, and a bag of word descriptor over shape is considered important for the pouring task, which is quite natural given a cup, for example, that the opening is important, and sort of most cups are rounded, so a bag of words descriptor should, a shape's descriptor should actually be quite important. For the lift up task, the opening feature is actually not that important, which is quite natural, but gradient and the bag of word descriptor are very important. For the handle task, gradients are again important, but the shape descriptor, the bag of word shape descriptor here, has increased quite much in importance. But also the free volume, which is the volume not enclosed in the grasp, together with the most similar shape primitive, is quite important for the handle, because most objects with handles so far have been cups and mugs, etc. And then we have corks, again, gradients, bag of words, and we see also an increase in primitive shape and kind of elongatedness, since most objects are actually like containers of some sorts. Since most objects with corks are actually containers of some sort. And if we have a quick look at the qualitative results, we see that we see here test examples to the left and the 5 closest neighbors. And what we can see is that KNN, for example, confuses a side grasp with handle grasp, but LMNM does not. Same goes for cork. The first nearest neighbor is actually a cork on a fluid container, while KNN chooses similar objects with similar form, which makes more sense. And finally, really shortly, we will have a look at some of the generated grasps. And as we can see, the images are quite noisy, but the red here are the palm of the gripper of the synthesized grasps, and to the right we see the 5 most probable grasps. And as you can see, they're all placed on the handle, for example. And here is one failure mode where the Saussure the algorithm gets confused and thinks that the right side of the Saussure is actually a handle. And also notice that the grasps are placed orthogonal to the direction of the ear, which is due to us not including any information about how the grasp is actually placed. And this is something we plan to address in future work. So, a bit from the conclusion, we have presented an approach for task-based grasping based on metric learning. We use demonstrations to learn a task-specific representation such that distance reflect grasp similarity. The learned task-specific representation keeps only relevant features for the tasks. And our approach allows a simple distance-based heuristics to actually transfer grasps from objects in the training database to novel objects. In future work, we plan to include information about how the human demonstrator grasped the object. And we also want to learn representations for relating the human hand to robotic grippers. I want to thank you all for listening. Any questions, please?